everybody, and welcome. This is one of our lectures about the heavy lift drone. We have a bunch of topics that we'll cover. This is one of the topics. If you are new to the heavy lift drone and don't know about it, with each of our lectures on a topic, we have placed at the end of the lecture an introductory lecture about the heavy lift drone so that you can learn about it if you want to. But everybody, we're glad you're here and welcome. Okay, and hello everybody, welcome, and we're glad you're here. We're talking about a heavy lift drone. This is our showing of it in a program called SketchUp. These little mannequins are about the same size as a human being. They're 6 feet tall. The drone will rise up on its legs, turn on its propellers. As it starts to spin its propellers faster, they generate enough lift for it to go up in the air. And when it goes high enough up in the air, it can add thrust to this set of propellers and rotate itself so it's now flying horizontally. And that is the heavy lift drone that has gotten itself in the air and is flying off. We feel with any drone, any heavier than air item that flies up into the air, there's a lot of parts of it that have to work properly. They're all important. We don't think that any one part is more important than the other, but you can't talk about all of them at the same time. So we're going to talk about them one by one. Here's a list we have of our topics. We do have an introductory video about this heavy lift drone that explains it in more detail. We're going to take that little lecture and put it at the end of all of our topic lectures so that if somebody comes across this video and doesn't understand what it's all about, they can watch the lecture at the end of the video. We would like to remind you any physically real object might hurt somebody. We suggest the actions of a physically real object should be safe and reasonable and legally allowed. Our advice is do not make any physically real object if you cannot properly control its actions. All right, and of course, welcome back. We are going to discuss the heavy lift drone in a series of topics. And the topic for this lecture is the propeller. And we'll go over here and show the heavy lift drone getting ready to go up in the air. There's 6 propellers on it. They're all the same. Because of the way drones work, this propeller turns in this direction to generate lift, and this propeller turns in that direction. This stabilizes the way the drone works. That's pretty standard drone design principles. The propeller spins around and moves the air. That activity generates a force on the propeller from the air, and that force is a force considered as lift. And if you have the weight of this structure with 6 propellers, if you take the weight of this whole structure and divide it by 6, and you get that amount of lift from each propeller, then you have enough lift for the structure to lift itself up off the ground. And actually, you want more lift than is the weight of the structure to get it to go up in the air and to actually get it to accelerate up in the air. We should note that while it would be nice if the propellers would just do everything, the truth is the propellers follow the laws of physics and the laws of aerodynamics. In general, most of the time, if you optimize the propeller for one particular type of aerodynamic function, then it won't be optimized for another one. And in this drone, we're going to propose a military use for this drone. So we want this drone to fly at a low airspeed. We want it to be able to take off from sitting still on the ground. and we want the propellers to be optimized to generate lift at low airspeed and to be able to generate lift when there is no airspeed. And there are a number of ways to figure out what a propeller will do. One way would be to simply create it and see what happens, but that's expensive. They have worked out math where you can describe a propeller using math, and then you can take and find out parameters about how the propeller should work based on the math. And frequently the math is very predictive of how the real propeller will work. One program that we have used is JavaProp. It creates discussion and opinions about propellers using math. It does not create the propeller, and it does not test it for you. It only tells you what it thinks the propeller will do based on the math that it is using. The program itself requires that you tell the program what is the mathematical description of the propeller you're talking about. You can, if you want, type in what you want the propeller to do and ask this program to design it for you. This will give you the geometry of what the design looks like that it created. Another option is to ask the program to import a propeller that you designed, and it wants to look at the chord of the propeller at a variety of places along the length of the propeller. It divides it into 20. And if you want to type in all this information, you can have this program import your document. And this is in a notepad format. And so if you take this notepad format and copy it, then if you click import, the program has seen what you said, and it will pull in the propeller for you. And this propeller is the propeller from this document. You can then go into this program and ask for information about this propeller. And the program will do analysis for you depending upon what you've specified. So it's 2 blades, it's this RPM, it's a 2-meter diameter propeller, and the spinner is that size, and we're looking at it at 32 meters per second of airspeed, and we're handing it 67,000 watts of power. With respect to propeller design, these are all parameters that come from the way that this drone works. It seems like when you add more blades, you don't really get more thrust. What happens is the total thrust of the propeller is divided among the blades, so you have less thrust pressure on each blade, but the propeller weighs more. We wanted low RPMs because we want to power this propeller with hydraulic fluid flow, and we want to have high pressure fluid for high torque at low RPMs. We tried to get a diameter of 1.5 meters, but we just couldn't get the power parameters to work. Remember, this propeller has 2 blades and it's 2 meters in diameter, which means that the entire propeller going from one tip to the other tip is 2 meters. So the blade of the propeller is about 1 meter. It's going to fly along at around 32 meters per second when it's up in the air. We're using the Rolls-Royce 250-C30 turbojet engine, which has a maximum continuous power output of 485 kilowatts. I should mention that this document is the European Aviation Safety Agency type certificate. So There's a lot of useful information about this engine in this document, but once you understand what its power output is in kilowatts, then you know how many kilowatts of power you can send to the 6 propellers. Basically, you can send 1/6 of the power output to each propeller. And once you have all of these parameters specified, you can get inside of this Java prop program, you can go over and have it look at parameters. You can analyze it with the power prescribed. So power is set at 67 kilowatts all the time. And we can look at a variety of pieces of information of this propeller based on this program. And this propeller, we want to look at when it's not moving at all. And it's at 1,810 RPM. It's drawing 67,000 watts. And it generates 2.59 kilonewtons of thrust, requiring 353 Newton meters of torque. And we will bring in this program from Unicon, Calculata. It's a conversions program, and we'll pull up the calculator. The heavy lift drone weighs about 2,400 pounds. We're going to assume that perhaps a 500-pound payload, so that's 2,900 pounds. So if we take 2,900 pounds and divide it by 6 propellers, we have to have 483 pounds of lift on each propeller. And this is the wonderful thing about this program. It prevents you from making all those stupid mistakes that are so irritating. We're looking for force, not power. So we'll go up here to force. We're going to add in pounds of force and see what it comes out in kilonewtons. So 483 pounds of force is 2.1 kilonewtons of force. So this is a wonderful program. And we'll knock all this out and go back over here. We have 2.5, which is bigger than 2.1. So under the theory, this propeller should give us enough force, 6 of them, to lift this drone off the ground, with the drone weighing 2,900 pounds. That's total weight. That's the drone weight plus the fuel weight plus the payload weight. We're putting in 50 gallons of fuel, which is 335 pounds of weight. There are a lot of considerations. One thing that's important to realize, in essence, because of the ratio of the height of the drone to the diameter of the Earth, the weight of the drone isn't going to change at any altitude that we care about, but the density of air changes. This program allows you to decrease the density or change the density of the air, so that when you go to your analysis, you can get values for the behavior of the propeller that are appropriate for the altitude that the drone is at. And of course, it's hard not to say when you're looking at this, well, is this real? And until you create the propeller, you don't know. There are very expensive programs that can give you better numbers, but that's not in my budget. I did find another propeller program, and the other program that I found is PropCalc, and it was, I thought, useful to compare this propeller in Java Prop to the same propeller in PropCalc. Java Prop divides the propeller into 20 different segments of the propeller, and PropCalc divides it into 10 segments, but you can go into Java Prop and get the chord and the angle or the pitch angle and the place on the ratio of the radius. So at 0.1, the angle is 63.4 and the chord is 313.8. So you can go over here to, well, we got to go down to 20. So 469, 496.9, 496.9. with an angle of 44.9 with an angle of 44. So you can take this exact propeller in this exact program and put it into this other program and see how it looks. This program seems to want to take the blade angle to -2 in order for them to agree with each other, but add a blade angle of -2 in this other program, you get about 25. The red one is power, so you're at about 6,700 kilowatts, and you're at about, the blue one is thrust, you're at about 2.5 kilonewtons. 2,500 newtons is 2.5 kilonewtons. So this program is agreeing fairly well with that program, and I thought that was reassuring. I guess I should mention this prop calc is using the Clark Y airfoil for the propeller. This program, I chose the Clark Y Reynolds number of 100,000 for the various different places on the propeller. So this Java prop is a more detailed analysis than prop calc, but at least they seem to agree with each other. And there's a lot of different power calculations that you need to do to prove to yourself that this is going to work at the different altitudes that this is going to fly at. But that is a separate lecture that I'm going to put in. That will be under the lecture of power. I'm going to show what the jet engine can do and what is needed from the propellers and how to get that power up there. I'm also going to address the issue that you need to be able to sequentially and in a minor fashion alter the power output of each of the 6 different propellers to keep the drone stabilized when it's in the vertical flight or hovering mode. That requires modulation of the power output. I'm going to get into that, but it's a separate topic. It's not about the propeller. And it seemed reasonable to me to say, well, okay, we got the propeller and we're happy with it and we have numbers on it and all that kind of stuff. But what is that propeller going to look like? That seems interesting to me. This is how it looks in this program. This is how it looks in that program. Not very satisfying. So I wanted to see, well, let's make a 3-dimensional drawing of this propeller. And to address the issue of creating a 3-dimensional version of the propeller, or at least a 3-dimensional drawing of it, we got to get back into SketchUp. And this is a kind of a busy slide. This is a propeller that came out of the design section of Java prop. It had great values with respect to numerics, but that's a weird looking propeller. I just couldn't convince myself that this was a good idea. So again, as you can see here, I have this listed as the AH80-140. That's actually the airfoil that we use for the wing, and this is mislabeled. This airfoil is the Clark Y. And so you can take, if you look at the printed output from the drawing program, it gives you the chord and it gives you the angle. And the way they tend to draw propellers is as though you were behind the plane and the propeller was going down this way. So if it's going straight down, then this line here is considered to be the line of 0 angle of rotation. So if this is 63.4, then instead of being 0 angle, it's at 63.4. So this number 1 segment at 0.1 of the ratio of the radius, which is 100 millimeters along the real rate. Notice that it's a 1,000 millimeter blade because the propeller is a 2-meter propeller, so each blade is 1 meter because it's a 2-bladed propeller. So it's at 63.4 degrees. And so that angle of 63.4 degrees is like this. And if you'll look at this one, this little segment here, this one is at 63.4 degrees. And that's how you draw this out. And the complexity of this drawing is that the chord for one segment of this segment is 448.3, but the chord of the other side of it is 642.8. So it goes from 448.3 to 642.8, and it decreases from 63.4 to 52.9. And so what you have to make is a segment that got longer as it went this way, and it also changed its angle of tilt. And it's not terribly complicated. You just have to do it, and then you stick them all together, you glue them all together, and you come up with a wing. Now, a propeller. This propeller here is the big propeller. I like this big propeller, but it's too heavy. You need to take the weight of the propeller and multiply it times 6 propellers, and it's too much weight. So we had to shrink it. And so we shrunk it down to this size of propeller. And what happens is you just don't get as much lift. And the motor that's going to be turning this propeller is the Parker Hannifin F12-60 hydraulic motor. And all of these drawings are to scale with each other. I wanted to be sure that this would really work. And so I'm showing this big propeller in gold, and in front of it is the little blue propeller, which is a little bit smaller. The weight of this propeller is a weight that's reasonable for this drone, particularly if it's made of carbon fiber. And I did put these little guys in here to show you this is 6 feet, just to give you some feeling for how big this propeller is. That's the big one. It is a 2-meter propeller, but this distance here, if we set it to inches, the maximum width of this cord is about 18 inches. So that's not so bad. And the length of it is coming out at 35 inches. And that is a 3-dimensional drawing of the propeller. And the last thing I'll mention is I think this is kind of pretty. It's just interesting to look at. I asked my drone guys, my mannequins, would they go out in the forest for me and just let me do a photo shoot to show off these propellers, and they said sure. And we all went out into the forest, and I told them to stand still and let me take a picture, and they said they would, so there you go. And I was able to get that to come out for something to be looking at. And this is the image that I created. I think it's kind of cool. Now, this is a 56 megabyte PNG image, which I'm going to try to get all of this up to my website so you can look at it, and you can download this 56 megabyte version of this image if it intrigues you. All the little images of it that I've used for thumbnails and LinkedIn and all that, those images are much smaller because they won't allow me to put in an image of that size. But if you like this, you can get the big version. And I can just show you, this is the home page of my website. That's a little guy that just watches over the website for me. Hi. Up at the top are a bunch of menus, and there's a lot of stuff I talked about a robot, but I also talked about stuff that's not a robot. and the heavy lift drone is not a robot. So you go there, and then you go to some of these topics I'm talking about. And this topic is the heavy lift drone topic. And if you click on that, you get out into the heavy lift drone. And I'll put all this new stuff about the propeller. This is the introduction section. And then the propeller section will be next. I'm going to send that up to my YouTube channel. And I'll also put this big image in there if you want to go get it. All right. Hello, everybody, and welcome. I'm glad you're here. Watching along. I plan a series of videos about all of the different parts of this heavy lift drone. This video is a very, very short introduction that I was thinking to put at the front of each video so that you kind of know where we are with the drone. I've got this bar marked off in feet. That's 240 feet. Here's the drone sitting on the ground. These little mannequins are here to show you scale. That's about 6 feet tall. The drone is sitting on the ground, not doing anything. It doesn't have all of its parts showing. I'll show you those in a minute. It powers up its engine and adds pressure to these hydraulic cylinders and stands itself up on its feet. It is not making any lift with its propellers. It then begins to add power to its propellers to generate lift, and it generates enough lift to go up in the air, and it's gone up about 50 feet. The two little guys are like just looking at it. And if you'll notice these struts, these legs that it was standing on, when it gets to 50 feet, it's beginning to retract these struts. Now, this is the most aggressive takeoff there is. I want to use this for a military purpose. It can actually go straight up for 3,000 feet, which is what I would do to keep it away from enemy contact with enemy fire. But if you're safe and happy about it and you just want it to go, this is how you do it. So at 40 or 50 feet, it begins retracting its feet. At 100 feet or so, it's got its struts curling up. Around 200 feet in the air, it has moved its landing struts to their fully folded up position. These guys were sort of watching it, and they're not really keeping up with it anymore. They're just talking. And up here, at this point, around 250 feet in the air, it puts significant thrust to these propellers, which rotates it up into a horizontal condition, and it can start flying. At 108 feet per second of airspeed, these wings have enough lift to hold up the drone. This is a little section where I demonstrate what the body of the drone looks like compared to a human being. The body of this has a aluminum skin. This skin is 1 millimeter thick. That I was working through the weight. This is some demonstration of the weight of this part of the skin, and I wanted to give a demonstration of this body is 12 feet long. That's how big it is compared to a person. This is how big it would have to be for a person to sit in it. There's a chance that this device may need vertical stabilizers to control yaw and horizontal stabilizers to control pitch. I'm hoping not. This is a proportion size drawing of the engine. The engine that powers the whole thing is the Rolls-Royce 250-C30, 600 horsepower. Here's a 50-gallon fuel tank. They're inside the drone body. This is the frame of the drone. It's been broken apart. This is a manifold system that I have that will control the flow to the rotors so that the rotors can bring the device in the air with controlled flight. Here are the wings. Again, 1 millimeter skin with their spars. This is a kind of a blown up drawing of the struts and their weight and how they're made. This is the various one. Now, this is not the right propeller. I'll get back to this. I did want you to see, here is a drawing of putting the fuel, instead of the fuel being placed in a big tank here. I'm sorry, that's the engine, that's the fuel. Instead of the fuel being placed in a big tank, it's a possibility that you could have 2 wing tanks. And I did want it to have a military use. This is the drone showing itself with the motor in place, the manifold in place, and I've placed 4 of my little smart motors in there. And so this is the drone, and this is the overview of it. And now we'll do some more details about all of the different parts of the drone.